Hello friends, today I will discuss the power relationships in a three-phase induction motor. In this case, first we will see what is the necessity of this power relationships, then the common terms that are used here, then the diagram necessary to analyze this, and then power stage diagram, and then relationship among them. The necessity of this power relationship in the three-phase induction motor is to find the performance of the three-phase induction motor and to find the various losses at various stages and also to find the efficiency of the three-phase induction motor. Here the major powers that are related or the relationships required are three. One is air gap power, the other is rotor copper loss represented by PC, and mechanical power developed represented by PM. And the terms that are used here are like this: stator input, stator core loss, stator copper loss, rotor input. This is also called air gap power, rotor copper loss, rotor core loss, mechanical power developed, friction and windage losses, gross output power. In this case, a rotor core loss is neglected because under running conditions the rotor circuit frequency is very low, so the effect of frequency on the core loss is very less, so core loss is neglected. This is the general diagram of the three-phase induction motor. The outer part is called stator, and this is the rotor, and this is the AC supply, three-phase AC supply given to the stator, and this supply gives the total input to the motor, that is stator input, and after that whatever comes out from the stator is the input to the rotor. First that enters the air gap, so that's called the rotor input. So in the stator also we find what is called the stator core loss, because the stator is made of laminations, and the other is stator also carries the conductors, so there are copper losses associated with that. Similarly, in the rotor there are copper conductors, so there is a copper loss in that. Similarly, the rotor is made of with the laminations, that is core, so core will also have the core loss but is neglected because the rotor circuit frequency is very less, and then the rotor will also have the friction and windage losses, and after that whatever is available on the shaft is called the total mechanical power output, that is called gross output. Before that, that's called mechanical output or mechanical power developed. If all those are represented in the flow in the form of flow diagram, it appears like this. This is the three-phase input to the stator represented by Pi, and this is the stator winding, and the stator winding will have, as I covered, it will have the stator copper loss, stator core will have the stator core loss, so it's written like this. So stator output will be the stator input minus stator losses. Stator losses means stator copper loss plus stator core loss. That is Pi minus these losses is the output from the stator. And the output from the stator is called the air gap power, that is also called input to the rotor. So here is the rotor, and rotor will also have the losses, that is rotor copper loss. So from the rotor input, if the rotor copper loss is subtracted, the output is called the mechanical power developed by the motor or rotor. And further, if the friction and windage losses are subtracted from this mechanical power developed, then whatever we get is called the gross output power, that is P naught. So in this case, the relation between rotor input, rotor copper loss, mechanical power developed is established. So input power to the rotor means it can be written like this: 2 pi ns t by 60. Here T is the motor torque and ns is the synchronous the three-phase induction motor synchronous speed, and this formula comes from general mechanical engineering, that is solid mechanics. So it can be written like this: 2 pi ns t by 60. Then power developed by the rotor can be written like this, that is represented by Pm is equal to 2 pi nt by 60. Here n is the rotor speed, whereas here ns is the speed of the magnetic field and torque is constant for this motor. So 2 pi nt by 60, this is the mechanical power developed by the rotor. Then since rotor copper loss can be calculated like this: rotor input minus rotor mechanical output or mechanical power developed. So then we get like this: 2 pi ns t by 60 minus 2 pi nt by 60. So if 2 pi t by 60 is taken out, then here ns minus n will come here. Then multiply numerator and denominator with ns, then we get like this, and then bring this ns below the ns minus n, so then we get like this, and transfer this ns to this part, then we get here 2 pi ns t by 60, and this is nothing but 2 pi ns minus n by ns is nothing but the slip formula. So this can be replaced with the slip, and the rotor copper loss can be written like this: S into Pg, and this 2 pi ns t by 60 is nothing but air gap power. This is called rotor input. It's already covered here, that is 2 pi ns t by 60, that is Pg. The same thing is written here, S into Pg. Then having known the mechanical power developed in the rotor, the equation can be written like this: rotor input minus rotor copper loss, which is represented by Pc, that is Pg minus Pc, but this Pc can be written in terms of the rotor input and slip like this: S into Pg. Then Pg taking out as a common term, then we get here 1 minus S into Pg. So having known Pm value and Pc and Pg, then the ratio of those can be written like this: Pg is to Pc is to Pm is equal to 1 is to S into 1 minus S. This means rotor input is highest value, and Pc means it is the rotor copper loss, which can be calculated by just multiplying the rotor input Pg with the slip of the induction motor. And to get the mechanical power developed by the motor, multiply the rotor input with 1 minus S. Let me summarize once. So we have seen how the rotor input, rotor copper loss and mechanical power developed are related. We have seen what is the definition of slip, and we have seen what is the general formula for the power, that is 2 pi nt by 60, and how that should be used for calculation of these powers, rotor input, rotor copper loss, mechanical power developed.